Hai, Assalamualaikum. Kami daripada grup 8 akan membentangkan tajuk Determination of Heavy Metals in Cooking Oil. Hai, Assalamualaikum. I am Siti KHADIJAH binti HASLAN, matric number A187249. Introduction. Cooking oils come from a variety of sources, including olive, rapeseed, peanut, grapeseed and mustard, corn and many others. Cooking oil must be monitored of quality and contamination. When cooking oil is heated, it can undergo many chemical changes, including oxidation of unsaturated fatty acid, triglyceride decomposition, and the formation of potentially cytotoxic oxidation products such as 4-hydroxytrans 2-nonenal (HNE) and other aldehydes that are purported to be associated with Parkinson, Alzheimer's, Huntington, arteriosclerosis, liver disease, and stroke. Acidity during long-term storage can also occur and associate with the content of polyunsaturated fatty acid content. Although this issue make use oil unfit for use in the kitchen and unhealthy for human consumption, it can still act as useful resource as a raw material for biofuel production, as there is a significant price difference between high-quality cooking oils and lower-quality biofuel raw materials. The possibility exists for unscrupulous people for filter and decolorized used cooking oils and sell them as high-quality cooking oils.
Chromatographic technique. Gas chromatography with flame ionization detection or mass spectrometry. Gas chromatography mass spectrometry has become an effective method for determining many of the organic contaminants that occur at trace concentration in complex food and environmental samples. It has been used for detecting pesticides in olive oil, cooking oil, or in fruit and vegetable because of the high separation efficiency of gas chromatography and the wealth of qualitative information and high sensitivity. High performance liquid chromatography HPLC. Liquid chromatography combined with mass spectrometry has made up the shortcomings of gas mass spectrometry in the analysis of highly polar pesticides due to its high selectivity, high sensitivity, and strong anti-interference ability, and has gradually become the first choice for pesticide residue detection in cooking oils or edible oils. These methods provide high resolution, accurate mass and high full-scale sensitivity and selectivity, making them a rapid, effective option for routine laboratories. Method. Detection technique for analysis. Various researchers deals with determination of metals in oil at trace, ultra-trace level using spectrometry and electrometric technique. Mentioned detection technique may be combined with some chromatographic systems. Oil has been analyzed from reference metal using atomic absorption spectrometer, inductively coupled plasma optical emission spectrometer, inductively coupled plasma mass spectrometer technique have become more popular since the early 1990s. HPLC mass spectrometry use mass spectrometry detectors, which are mainly used in provincial quality inspection institutions, scientific research institutions, and a few large enterprises. Its detection is highly sensitive, accurate, and reliable, but it relies on expensive instrument, reagent, strict environmental conditions, and professional operators. Therefore, it is not suitable for on-site rapid testing of cooking oil, while suitable for laboratory testing. One method, based on a universal lipid analytical method, separate the majority of analyte by reverse phase. We focus on triglyceride and their composition, diglyceride, and minor component. A second RP-HPLC method quantifies the free fatty acid resulting from base hydrolysis of the sample with detectable change in fatty acid composition. A third method, using normal phase NP-HPLC, separate the samples by lipid class, including TAGS, free fatty acid, and DAGS, a faster and simpler result than the first method. The charge aerosol detector is ideal for this analysis based on its relatively uniform response factor for non-volatile analyte and its high sensitivity. The detector operates by nebulizing analytes after they elute from the column and placing a charge on the resulting analyte particles. Peak area is proportional to the amount of analyte mass entering the detector. Typical limit of quantitation are in the single-digit nanogram on column. A replicate injection precision value are 2% relative standard deviation on peak area. A fourth method for aldehyde determination using HPLC with fluorescence FLD and mass spectrometry of derivatized oil sample is also described with associated result. Identification of aldehyde degradant component were made by mass spectrometry.
Procedure: RP-HPLC Corona Ultra RS Universal Lipid Method. Sample preparation: 100 microliter or equivalent mass of sample dissolved in 900 microliter methanol or chloroform. Ratio 1:1. RP-HPLC Corona Ultra RS method for omega lipid or free fatty acid. Sample preparation: oil samples 50 microliter aliquot were dissolved or dispersed in 5 ml isopropanol water, ratio 3:2, and 1 ml of 5 mKOH. All samples were heated in 80 Celsius water bath for 1 hour with occasional stirring. After samples were cooled, a 500 microliter aliquot was removed and 25 microliter of formic acid was added to neutralize the sample. NP-HPLC Corona Ultra RS method for acylglycerol and free fatty acids. Sample preparation: 40 microliter or ml of oil were dissolved in isooctane or isopropanol, ratio 95:5. Aldehyde analyzed by reverse phase HPLC with FLD and MS detection. Sample preparation: a 500 microliter aliquot of oil sample solution, 10 mg or milliliter in tetrahydrofuran was mixed with 1000 microliter of Hans reagent in a 1.5 ml centrifuge tube. The solution was heated at 75 Celsius for 1 hour. Sample was centrifuged 10,000 grams for 3 minutes, and the supernatant was transferred to an HPLC vial. The Hans reagent was prepared as follows: 50 ml of denatured alcohol and 1 ml of water was mixed prior to the addition of 2 grams of ammonium formate. Once dissolved, a 1 ml volume of formic acid and 50 mg of 1,3-cyclohexanidine was added. The solution was brought to a 20 ml volume through the addition of denatured alcohol. Data for chromatography technique. Figure 1 shows the example of HPLC corona detector chromatogram of unused soybean oil and 5-coltor oil normalized to the ECM46 peak. And table 1 shows relative peak area analysis of 2 unused soybean sample and 5 gutter oil sample.
Discussion. Each technique has some special requirements, advantages and disadvantages according to its basic principle. It is a sensitive, proper for direct introduction of all samples in the form of emulsion and does not require a large amount of sample. Mass spectrometry have a requirement of sample pretreatment but is more sensitive. There are scarce researchers dealing with all samples related to voltammetric and potentiometric technique. The temperature program was set up from 50 degrees Celsius to 250 degrees Celsius with 4 degrees Celsius over minute. Both the injector and detector temperature were 280 degrees Celsius and it was used as a carrier gas. The injection volume was 2. Ionization energy was used for mass spectroscopy detector. A main source of oil pollution is in the long-term and large-scale use of chemical fertilizer and pesticide during crops cultivation. The use of fertilizer and pesticide containing heavy metals such as lead, mercury, cadmium, arsenic and other harmful substances have caused the oil to be polluted by heavy metal during the growth process. These pollutants are partly transferred into the oil during production, causing the pollution of cooking oil. Found that heavy metal were extremely stable in the ecosystem and were easily enriched and amplified in the food chain. Analytical method of gas chromatography mass spectrometry detection appears to be appropriate for simple and rapid detection of multiple bond in fatty acid methyl ester chains in oils. Recently, some oils have become available as the extraction technology. Gas chromatography has been improved.
My name is FATIHAH and I'm going to tell about the aim of study. The first one is to determine the concentration of heavy metals such as copper, zinc, cadmium, lead, iron and manganese in edible oil sample, including rapeseed, soybean and linseed oils. Second is to determine the variation in heavy metal concentration in different oil fraction. The sample preparation for analysis is sample obtained from the producer was stored in polythene bag in a shade placed at room temperature. The analysis was performed on rapeseed, soybean seed and linseed and in their fraction. The first fraction is pressed raw oil. The second fraction is extraction oil before degumming. The third fraction is pressed natural flavor oil. The fourth fraction is pressed bleach oil. And the last fraction is pressed refined oil. Each sampling group fraction came from the same production lots. Next is extraction technique. Acid extraction or extraction using specialized agent are used in the sample preparation. Under the ideal extraction circumstances, after the extraction of metal from oil with nitric acid, hydrochloric acid or acid mixture, the extracts are analyzed. Although the extraction process has advantage in both the separation and pre-concentration of metal in oil samples, the recovery are typically insufficient for a large number of metals. Simple acid method for determination of trace metal in oil and fats. The method has been performed with the use of ultrasonic intensification and successfully applied for accurate determination of iron, copper, nickel and zinc in oils. The next one is procedure. In the first stage of refining oil, pressed raw oil is obtained by grinding rapeseed and roast the mass, which is then humidified and conditioned. The increased temperature of raw material is favorable for the decrease of metal content. When oil is originally extracted during hot pressing in one process, tissue structure is destroyed. Pomade and dried distiller grain are byproduct of the oil processing, including the subsequent step. It should be underlined that harmful compounds other than heavy metal are introduced to pomade and dried distillers grain throughout the production process. The second stage is the process of oil extraction, involve its multiple rinsing from seeds using the solvent. The extraction of second fraction is produced after the solvent is distilled and before degumming. Pressed neutral flavour oil, which is the third fraction in the production, is marked by lower concentration of metal in comparison to the second fraction. Obtaining the fraction involves oil hydration, removal of protein slime, and phosphate and deacidification using nitrogen hydroxide. The fourth fraction is bleaching. It is aimed at the removal of dyes such as chlorophyll, anthracene, and carotenoid, which give the oil their dark color. This refers especially to the chlorophyll dyes, which, apart from dark color, accelerate oil oxidation. This process additionally removes polar substance remaining after the process of deacidification. In the process of bleaching earth oil, active carbon or aluminium oxide are used in order to absorb the given polar substance. And the final stage of oil refining is deodorization, which gave the product its final quality of refined oil. The process removes from the oil the substance responsible for unpleasant smell and taste, such as lower fatty acid, aldehydes and ketone, hydrocarbon, and sulfur compounds. The separation of the substance requires the use of distillation with water vapor under reduced pressure as the boiling temperature of those compounds. As a result of this process, the fifth fraction is obtained, which is the final product ready for the consumption.
Madam Shamiti Rizal would like to discuss about result and discussion. There are three tables of result. Table 1 shows the concentration of heavy metal in the production fraction of rapeseed oil. The second table shows the concentration of heavy metal in the production fraction of soybean oil, and the last table shows the concentration of heavy metal in the production fraction of linseed oils. Result and discussion. The seed of oil plants and the fraction which are characterized by different properties were analyzed. First of all, they require different method of cultivation and they differ in terms of seed fatty acid content and the ratio of saturated and unsaturated fatty acid. Besides, the variability in metal concentration is related to the fact that they can occur in plants and intermediate products as metal ion or metal complex, and they can be characterized by different oxidizing activity. The highest concentration of each analyzed heavy metal were observed in zero fraction. This is due to accumulation of heavy metal in the untreated seed. The highest concentration between 49.7 and 64.8 depends on the type of seed were shown for iron. Relatively high concentration were also obtained for manganese and much lower concentration were presented for copper and lead. The rapeseed was characterized by the higher concentration of zinc, iron and lead, where the linseed by the highest concentration of copper, manganese and cadmium. Besides, the lead concentration shown for the 5 analyzed fractions were below the limit of detection. Next, the oil obtained during the process of oil extraction, the second fraction were characterized by high contamination because at this stage also other elements were extracted. Besides, higher temperature may influence the leaching of metal from the intermediate product. For this reason, the highest concentration of cadmium and lead were observed in the second fraction. The concentration of other analyzed heavy metal was slightly lower. The significant lower concentration was shown for the next fraction. The fourth fraction, pressed bleached oil, was obtained after the process was conducted at increased temperature. As a consequence, the concentration of copper, zinc, and iron for every analyzed sample was slightly higher. The final stage of oil refining ready for the consumption is the refined oil. The process was conducted under produced pressure. We favor the removal of metal. The free fraction was characterized by the concentration of metal below the limit detection. They are the lowest concentration and they are similar to the dose reported in literature. This fact proves good quality of analyzed oil. Conclusion: the selected analytical procedure allows to obtain repeatable and accurate results relatively quickly. A similar trend in the concentration variability of the analyzed heavy metal, iron and manganese in rapeseed, linseed, and soybean oil sample during production was observed. The final products are characterized by low concentration of those heavy metal. The technology used in oil production effectively removes excessive concentration of iron, manganese, and zinc from the raw material.